Unlimited free energy identified. Lightning. Okay. I've been getting a lot of controversy over my interpretation of what lightning is and where it comes from, and it's very simple. And I'm going to help you to understand this. After you see this video, you'll know and understand all of the lightning that we see. Okay. First of all, you have to understand about the clouds. Now, here in Hawaii, I can observe the clouds in the evening, and they'll go drifting overhead, and as the sun sets, they'll start to just evaporate, disappear. And this is because, and of course the moisture within them also disappears. It just dissolves and evaporates into the air, spreads out into the air. What happens is the sun, as it sets, the sun's solar radiation that was hitting the cloud previously is gone. So there's nothing to keep that cloud warm. And so the cool air around it absorbs the heat, and so the cloud ceases to exist. So clouds are really just pockets of warm air. They're just floating around there. They condense the moisture. So if you see a cloud, it's generally warmer air than the surrounding air. It's not always the case. Of course, there can be warm clouds there can be warm air without clouds. Okay, now let's go into the winter time here. You noticed in the winter time, when it's clear, how the temperatures can be very low, and when it gets cloudy, it actually warms up. And this is telling you again that the clouds contain some heat. Now, lightning, the typical lightning we see in a thunderstorm. What you're looking at is the clouds, which are full of moisture and warm air. They come and they intersect big masses of cooler air. And so this cooler air rapidly cools the warm air in the cloud. Now, hello folks, there's got to be something keeping that cloud warm, right? It's energy. It's heat. What is this energy? Well, it's electricity. And very clearly what happens is when the warm cloud is rapidly cooled, the heat, the energy, the electricity has nowhere to go. It's because it's cooled so rapidly it can't disperse into the air. So this huge amount of heat, electricity, it's discharged in electrical discharge, which would be the lightning. Now, I can take this a little one step further, because have you heard of lightning when there's absolutely no clouds? You probably have. This is simply the same thing. A big mass of warm air collides with a big mass of cool air. The warm air cools down rapidly, and that heat, normally it could be absorbed, but because it's cooled so rapidly in such a huge quantity that electricity, the heat, condenses and forms lightning. Okay, can anybody tell me what you're looking at here? Does that look like lightning and clouds? Actually, no, it's not. It's lightning in a volcano. Oh, is there something new? What in the world could be causing lightning in a volcano? Gee, could it be the dust on the water molecules, the water atoms, or what is that? Well, we know, don't we? You have some superheated gases and dust particles coming out of the ground, thousands of degrees, and they're interacting with the cooler air on the outside. So what happens to these hot gases when they come out and they're rapidly cooled? Well, you can see here in Iceland, some of these photos are from Iceland, Japan, and Chile. And over the last 4 years, these photos were taken of volcanic eruptions. And don't they look familiar? They remind you of something? Do they remind you of a Tesla coil? Yes, you're seeing basically the same effect. You're seeing the electrical discharge, the heat, is being condensed in electricity. And so there you have it. It's right there where you can see it. And interestingly, the University of Florida and New Mexico Tech are doing research to find out what in the world causes this lightning inside of volcanoes. It's a great mystery for them. And I contacted them. I contacted Ronald Thomas with the New Mexico Tech, and Mr. Human and University of Florida, and they never got back to me. I tried to explain to them what was causing this. It's very simple, but they weren't quite ready for it yet, or maybe if they found out what was causing it, then they would have to cut their funding for their research, and they probably enjoy all that money they're getting. Okay, let's look at another proof. This Lichtenberg acrylic lightning. What they have here is a piece of clear acrylic, and before he hit it with his hammer and nail, it was just clear. You couldn't see anything in it. It's just like our air. You can't see anything in it. You can't see the heat. You can't see the electricity in our air. You can't feel it. You would never know it's there unless you condense it. So what's happening here is this piece of acrylic is impregnated with electricity, but it's all dispersed. It finally dispersed throughout the whole piece of acrylic, so you don't know it's there. They take a nail, they tap it in one side, and it causes all of that electricity to start to condense. And as it condenses, thicker and thicker and heavier and higher voltages and more amperage, it approaches the nail there. And you can see the pattern is identical to what you see in a Tesla coil or what you would see in lightning, and it's the same thing. That it's not traveling from the thick part out to the thin part as it appears. It's actually going from the thin part into the thick part. So when you see lightning, where the lightning is the brightest is where it's condensing the most. That's where it's going to. The lightning is traveling. So I think this is really amazing that someone was able to invent this, so we can actually see, where this is coming from. And now imagine our air has heat. That heat is electricity, and if you condense that heat, electricity, you have surplus energy. And you've seen it in the volcanoes, you've seen it in the clouds, and you're seeing it here as another example. One more thing I'd like to mention is that if you look out your window, can you see how warm it is? No, you can't. You have to go out there and feel it. But just because you can't see that energy doesn't mean it's not there. So we're surrounded in this heat, and we should learn to appreciate that, because it's usable energy. It's a very powerful form of energy. And because I'm right about this and I've taken so much ridicule, I'm going to have some dessert.